Solving exponential equations. So here's the bottom line. We got variables in our exponents. It's a little bit different than what we have always worked with before, but hey, now we're stepping up the game. Now, but here's what we can do. If we can get to the same base of which the exponent is being raised, we can then cancel the bases and solve for the variable in the exponent, which is pretty cool. So let's kind of work through this first example where we got 4 raised to the power of 2n minus 1. And obviously we're going to be trying to solve for n. What does n equal? And then we got 64. Now I want to think about getting this 64 to a base 4. And if I do that, then I can cancel the bases and solve for the missing variable. Well, let's see. 4 times 4 times 4. 4 times 4 is 16. 16 times 4 is 64. So we can now rewrite this as 4 to the 2n minus 1 equals 4 cubed. Can you agree with that? 4 cubed. Now, we can cancel the bases and just work with our exponents and solve for the variable. So I got 2n minus 1 now equals 3. And we're going to add 1 to both sides where we got 2n is now equal to 4. And n is equal to, after dividing by 2, 2. Now, I might want to plug that back in and see if that seems to work out all right. So if I substitute 2 for n, let's do this. We got 4 raised to the power of 2 times 2 minus 1. And that's going to equal 4 cubed. And shazam, 4 cubed is actually equal to 64. So we want to get to the same base, cancel the bases, solve for the variable in the exponent. Now here we got 5 raised to the power of 5x, and that equals 125 raised to the power of x plus 2. Now, this kind of involves a different step, but initially I want to do the same thing. I want to think about this 125. Can I get it to a base 5? Well, 5 times 5 times 5. 5 times 5 is 25, times 5 is 125. So I can write this in as 5 raised to the power of 5x. That stays the same. Now my base, I got base 5 raised to the power of 3 times x plus 2. And you can see I'm going to have to distribute that 3 to the x plus 2. But now I can cancel my bases. And so we got 5x. Writing that as an exponent. 5x equals 3 times x plus 2. And then we distribute that. I still got 5x is equal to 6x plus 6. Okay, so we got variables on both sides. We're going to have to subtract 6x. I'm going to go ahead and subtract 6x. And now I got negative x equals 6. And we're going to divide by negative 1 where x is equal to negative 6. So let's see how that works out. Okay, so if I substitute in 5 times 5 raised to the power of negative 6 equals 125. No, I need to get that back down to base 5. 5 times 3 times negative 6 plus 2 negative 4. You know what? I made a huge mistake. I knew something didn't look right. 3 times x plus 6 is not 6x, it's 3x. Let's erase all this. I was feeling kind of queasy about that. Something didn't seem right. We're going to subtract 3x, excuse me. So now we got 2x equals 6 divided by 2, and x is equal to 3. Now that should be better. Okay, let's see. If we come back in here and substitute this, taking our 125 down to a base 5. So I got 5 raised to the power of 5 times 3. That's going to be 5 to the 15th. And then we got 5 times 3 times 3 plus 2. And shazam, both of those would be 5 to the 15th to 5 to the 15th. That's going to be a pretty large number. I'm just kind of curious. I wonder what that is. Sometimes it just pays to be curious. 5 raised to the 15th power. Oh, wow. 3.05 times 10 to the 10th power. Means there's 10 zeros after that 3. 6 zeros is a million. 9 zeros is a billion. That's going to be 30 billion. 30 billion. Probably what our government spends every day. All right. Be careful. I almost made a big mistake. But thank goodness we caught it. How did I catch it? Because I was trying to prove my answer. Substituting back in and I saw, uh-oh, something's terribly wrong.